Yes, good evening. This is the question that we are asking here. Wheatstone bridge or it is a Wheatstone network. The question is, derive an expression for the balanced condition in a Wheatstone network. Either it is called by the name the network or it may be taken as the bridge. And this is the name of a scientist. Wheatstone is the name of a scientist who has detected all these things and who has written all these concepts. And using the network analysis theorem that we are going to take up all these things, and Wheatstone network, it is a particular bridge or maybe a network. Usually we are using in the case of post office boxes or maybe in the case of meter bridge experiments that we are using the same principle. And here, to solve this idea, I have chosen 4 resistances here, P, Q, S, R. Again I can repeat, 4 resistances P, Q, S, R are connected in cyclic order to form a quadrilateral. I have chosen 4 resistances P, Q, S, R. They are connected in a cyclic order, end-to-end connection to form a quadrilateral here, and it is forming 4 nodes here. Nodes means 2 or more junctions, 2 or more wires or maybe the conductors. If they are joined together, that particular point is called by the name the node or a junction. So this is one junction, another junction, one more node. So A, B, C, D are the 4 nodes or the junctions. Between A and C nodes of the junctions, we have connected a battery whose EMF is equal to capital E. In turn, that we have connected a plug key also. It is just acting as a switch. Either it is switched on or switched off. For that purpose that we are using a plug key. And here, as soon as if we are connected a battery here, there must be a potential difference to current flow. Let us consider, let us choose. This point is having the more potential. This point is having the lesser potential. B is having the higher potential, D is having the lower potential. Because of that one, there is a current starts to flow from B to D. So B to D, whatever the current is flowing, I will take it as Ig here, because capital G is the resistance of the galvanometer, and the galvanometer, whatever we have connected from B to D, between the terminals B and D, we have connected a sensitive galvanometer to measure a small amount of current. Even though if it is said to be a small current, it can assess, it can measure. For that purpose, we are connecting a galvanometer. Inside the galvanometer, there is a resistance here, opposition for the flow of current. That resistance is said to be taken as capital G. Here, current is flowing from B to G. I will take that one as Ig current here. And this is the main current drawn from the cell. In a circuit, current, whatever it has been drawn from the cell, that particular current is called by the name the main current in the circuit. So this is the main current. Up to here, it is a main current. Using the Kirchhoff's current law, it has been divided in the form of I1 and I2 here. I will write this is I1 and this one is taken as I2 here. Therefore, I is equal to I1 plus I2. I is the incoming current. I1 and I2 are the outgoing currents. Sum of the incoming currents is equal to sum of the outgoing currents. Therefore, I is equal to I1 plus I2. Up to here it is I1. Once it is reaches here, again it is divided into branches here. So one branch current is I3, the other branch current is Ig. So at this particular point, incoming current is I1. I1 is equal to here Ig plus I3. So this is at the point B point here. So this is at the point B here. I1 is the incoming current. I1 is equal to outgoing currents are I3 and Ig here. I3 plus Ig using the Kirchhoff's first law, current law. Therefore, here I can write I3 is equal to here I1 minus Ig. Therefore, I3 is equal to I1 minus Ig. This is the current, whatever it is flowing through the galvanometer. Current flows through the capital R. Now these two are joined together and it is forming I4 here. Therefore, at the point D here, this is at the point D. Again using the KCL, I2 plus IG together it is forming as I4. So this is I2 plus IG. So this is I4. I2 is flowing here, IG is flowing here, joined together to form I4 here. Therefore, I4 is equal to I2 plus IG. According to KCL here. This is from KCL. Kirchhoff's current law. Now I am supposed to consider Kirchhoff's voltage law here. I will going to consider the voltage law, Kirchhoff's voltage law, Kirchhoff's second law. I will apply that particular law for this particular mesh. This is a mesh. A mesh means it is a closed path in which the current is flowing here. I will choose. This is said to be a one mesh. So I will apply, okay, applying KVL. Okay, one by one let us consider. Applying KVL for the mesh. I will take one mesh here, A, B, D, A. This mesh. This is a mesh. A, B, D, A mesh. Already we know the Kirchhoff's second law. I will apply the Kirchhoff's second law now like this. Whatever the currents are flowing like this, I will take it as positive, positive. Along my direction, whatever I am showing, if it is said to be in the same direction, taken as negative, positive. Opposite direction must be taken as negative. See that? I1 clockwise direction, positive. IG clockwise direction, positive. IG is positive. Whereas this I2, it is coming in the opposite direction, therefore I will take that one as negative. This is basic idea. I1 multiplied by P, I1 into P, current into resistance, current into resistance, current into resistance, and this current into this resistance. Here there is no EMF. If there is no EMF, it is equal to 0 we are supposed to write. Similarly, okay, how we are going to write? I1 positive current. You can consider here, whichever the currents are flowing like this, we have to take it as positive. Opposite direction current, we have to take it as negative. So here I1 into P, I1 into P, this is IG into G plus IG into G, current into resistance, algebraic summation is equal to sum of the EMFs. So here I1 into P, positive current, resistance, positive current into resistance, IG into G is finished. Now it is coming here minus I2 into R. Minus I2 into R is equal to some of the EMFs we had to write here. Here there are no EMF, no batteries are connected here, no cells are connected here. Therefore I will take that one as 0. This is one concept. Equation number 1. Equation number 1. Next one for the mesh. One more mesh. This is the mesh I will going to choose it. Clockwise direction here also we consider. B, C, D, B. This is the mesh. B, C, D, B mesh. This is the mesh. This mesh I will going to choose it. B, C, D, B. And don't forget, whenever if you are writing a mesh, if you have started with one particular node, you have to end with the same node. B, C, D, B. I have started with B, ended with B. Here, A, B, D, A. You can observe that A started with that one, ended with A. Then only it is a closed path. Then only it is closed down. Then only the current it starts to flow. There it is. If it is break is there, it will not flow. Open circuit, current will not flow. That is the meaning. So here for the mesh BCDB, I3. Otherwise directly you can write I1 minus IG, no problem. I3 into this, current into resistance. I3 is flowing in the clockwise. Minus I4 here, you can observe that it is coming like this, like this, like this. Now it is coming in the opposite direction, therefore I4 is negative, going like this. Ig is negative. A very crucial thing, important idea. Let us consider like this. Whichever the currents are flowing like this, we have to take it as positive. Opposite direction currents are taken as negative. I3 positive, I4 negative, Ig negative. Again I can repeat. I3 positive, same direction. Opposite direction I4 negative. Opposite direction Ig negative. Then multiply with the resistance. That's all. Q is the resistance, S is the resistance, and the capital G is the resistance. Now therefore, here I3 into Q, positive value, minus I4 into S. If you don't want to write I4, directly you can write I2 plus Ig. Okay. Minus I4 into S. Here it is. Okay. Minus Ig into G. It is equal to 0. Because here again there is no battery or no cell. Since there is no cell is connected here, I will take that sum of the EMFs is taken as 0 here. And in this case, again, I3 value, substitute for I3, I1 minus Ig, I1 minus Ig multiplied by Q minus I4 value, I2 plus Ig. I2 plus Ig, this negative sign as it is, bracket it is to be enclosed, minus Ig into G is equal to 0. Right? I will take this one as equation number 2. Equation number 1 is there, equation number 2 is there. The same idea we are using even in the case of meter bridge experiment also, it is a sliding contact. Here, just like a post office box or maybe the Wheatstone network, what we are doing is, we are adjusting the resistances P, Q, S, R. P some amount, Q some amount, S some amount, and R some amount. If you are increasing the resistance or decreasing the resistance, at one particular stage, current flowing through the Ig is go on decreasing, decreasing, decreasing. Still, if you are adjusting this P, Q, S, R, P, Q, S, R are the resistances. We can adjust them. If you are adjusting them so that Ig current go on reduces and galvanometer shows almost equal to 0, and once in a way it is going to show exactly it is equal to 0. Once galvanometer shows 0 here, current flows through the galvanometer is equal to 0. That means to say that Ig current is equal to 0. So what we have to write here? So by adjusting, one is P, the other one is Q, the third one is R. S and R. By adjusting P, Q, S, R resistances, galvanometer may show, it has to show of course, 0 deflection. If it is showing 0 deflection, then I can say immediately Ig current is equal to 0. The current flows through the galvanometer is 0. As Ig current is equal to 0, we can substitute that Ig is equal to 0 in equation number 1 as well as in equation number 2. So, put Ig is equal to 0 in equations 1 as well as in 2. First I will take this. Ig current is 0 here. I will put 0. 0 into anything is 0. Therefore, you are going to have equation number 1, I1 into P plus 0 minus I2 into R is equal to 0 here. I1 into P, written, Ig current is 0, minus I2 into R is equal to 0. Therefore, shift this one to the other side. I1P is equal to I2 into R. I will take it as equation number 3. Same idea, put Ig current is equal to 0 in equation number 2 here. So in this case here now, I1 minus Ig, where Ig current is equal to 0, I1 minus 0 into Q minus I2 plus 0 into S minus Ig current is 0 into capital G is equal to 0. So wherever Ig is there, you go and put 0. So therefore here it is I1 into Q minus I2 into S is equal to 0, and I1Q is equal to I2 into S. Shifting this one to the other side, I will take this one as equation number 4. Next concept, divide 1 by the other. Equation 3 divided by equation number 4. So what it gives? I1P divided by I1Q. This is I2R divided by I2S. I1 get cancelled. I2 get cancelled here. Therefore, P by Q is equal to R by S. This is the balanced condition. Okay, derivation is completed. Derivation is completed, but we can ask series of one more questions here. If it is a balanced Wheatstone network, if it is a balanced Wheatstone network, P by Q, P divided by Q is equal to R divided by S. P by Q is equal to R by S. If this is holds good, then automatically Ig current is equal to 0. Vice versa. If Ig current is 0, P by Q is equal to R by S. If P by Q is equal to R by S is holds good, Ig current is 0. There is a balanced condition. Point number 2. In a balanced condition, if I am cut down this wire if it is cut down, galvanometer, now balanced condition will not change. Point number 3. Instead of galvanometer, if I am putting a high resistance or very low resistance under balanced condition will not change, because anyhow current flows through the galvanometer is 0. Under balanced condition, point number 4 or 5, under balanced condition, galvanometer and battery these two are interchanged here. Under balanced condition, I will take galvanometer and I will connect here. I will take the battery and I will connect here. Same balanced condition you are going to get, but in a reciprocal of that you are going to get. So therefore, under balanced condition here, Ig current is 0 and P by Q is equal to R by S. Using that idea, we can solve some problem. Immediately, if we are seeing P by Q is equal to R by S in a problem, directly we can say Ig current is equal to 0. If P by Q is not equal to R by S, P by Q is not equal to R by S, it is not a balanced condition. If it is not balanced here, then we are supposed to determine Ig current is equal to how much in the case of problems.